Hello guys, so from this video we are going to start the lipid metabolism, and in metabolism we mainly focus on the fatty acids and cholesterol and lipoproteins. So first start from the fatty acid, and fatty acids are synthesized and degraded. When we study the synthesis and degradation, this is called the fatty acid metabolism. So fatty acid metabolism we start from the synthesis. Okay, so if we want to synthesize the fatty acid, okay, and we know and that when we in the next videos we are going to study about the integration of metabolism. Integration means we have carbohydrate, we have lipids, we have proteins. These three can be interconverted into each other, okay, and this study in the interconversion of fatty acid, lipids and carbohydrate, this interconversion is called and the integration of metabolism. Okay, so in the coming video I will tell you how these are integrated, and there is an example here in this video that we know the acetyl CoA. I show you acetyl CoA in the is the one which go to the TCA cycle and then form the state with the when it is combined with the oxaloacetate. Okay, so this I'm showing you again. Then when we have pyruvate from the glycolysis, the TCA cycle start when pyruvate converted into acetyl CoA. This acetyl CoA combined with oxaloacetate to form state. So acetyl CoA is a intermediate of the degradation of glucose, and glucose is what? Glucose is a carbohydrate. So we know that acetyl CoA is intermediate of it is an intermediate of degradation of carbohydrate. So this carbohydrate is going to convert into lipid, which is fatty acid. So we are going to study this. First we should know that fatty acid synthesis, fatty acids are synthesized from the acetyl CoA. Okay, how we are going to see this? Okay, so first thing, if we want to add if we want to synthesize the fatty acid from the acetyl CoA, first thing we should do is that acetyl should be transported. You know, this TCA cycle and pyruvate conversion to acetyl CoA, this whole thing is occur in the mitochondria. Okay, but we know that fatty acid synthesis occur in the cytosol. Why? Because the enzymes for the fatty acid synthesis are present in the cytosol, but we have acetyl CoA which is the precursor for the fatty acid. So we should transport this acetyl CoA to the cytosol, from mitochondria to the cytosol. Okay, so transport is from mitochondria to cytosol. And who help in this transport? We should only know who will help in this, and this is done by straight. This is done by straight rate. How? In the first reaction, this is acetyl CoA combined with oxaloacetate to form the straight. Okay, so like this we are going to combine oxaloacetate combined with acetyl CoA to form straight. Okay, when this reaction occur in the mitochondria, this state can pass the mitochondrial membrane to come to the cytosol. Why would done this reaction? Because acetyl CoA cannot cross the mitochondrial membrane. So that is the reason that for the crossing of the inner mitochondrial membrane, acetyl CoA first should be converted into state which pass the mitochondrial membrane. When this come into the cytosol, this reaction is done backward, and we get the acetyl CoA in the cytoplasm. So first is transport is done. Then when we have transported this acetyl CoA into the cytosol, then we convert this acetyl CoA into malonyl CoA. How? We know the acetyl CoA is a 2 carbon compound, and malonyl is a 3 carbon compound. Okay, so conversion of 2 carbon to 3 carbon, we need a 1 more carbon. And who will supply this 1 more carbon? Yes, carbon dioxide. So carbon dioxide is one which is going to supply in this reaction to form the malonyl CoA from the acetyl CoA. Okay, and whenever we have carboxylation reaction, we know there is a vitamin B7 which is the biotin. Biotin is used here. Okay, and this reaction is done with the help of enzyme which is called carboxylase. For the carboxylation, there is an enzyme for the which is called carboxylase. So enzyme name is on which substrate we done this carboxylation on acetyl CoA. So enzyme should be acetyl CoA carboxylase, acetyl CoA carboxylase, ACC. And this is the regulatory step of the fatty acid synthesis. We should know that this is the very important. Why? Because this is the regulatory step of the fatty acid synthesis. Okay, so in the MCQs they can ask which is the following enzyme is the regulatory enzyme of the fatty acid synthesis. So option will be the right is acetyl CoA carboxylase. Okay, so when we have done the acetyl CoA conversion to the malonyl CoA, the next thing is called fatty acid synthase complex. What is this? We are going to study. This is the complex. So complex enzyme consists of many more enzymes. So these enzymes I'm going to tell you. So the sequence of this reaction should be like this: reduction reaction, dehydration, and then again reduction. Okay, why? Because this will help you in the memorization of this, and also in the next step in which we degrade the fatty acid in the beta oxidation reaction. Okay, this will also help you in that reaction. Okay, so we have reduction, dehydration, reduction. So these are lot of intermediate. How can we remember these lot of intermediate? You don't need to remember if you want to get the MCQs problem. Okay, these are not going to ask from you. If you have a short essay question, okay, if you have a question in the written form, they can ask from you the how fatty acid are synthesized. Okay, if you don't want to do this synthesis, if you want only MCQ, then the thing you should remember is the transport by the straight and carboxylase. This enzyme is the regulatory enzyme, and you just need to remember, you just need to see this reaction but not to remember these reaction if you want only MCQs. Okay, for the USMLE lab. So first reaction is acetyl CoA and malonyl CoA. These are, look, we have acetyl CoA, okay, which is transported, and we also get malonyl CoA from the acetyl CoA. So when we get these two, we combine these two to form ketoacyl. Okay, which then is further converted into hydroxycyl, and then which is converted into transenol ACP. Okay, we just why I'm using ACP because this is a carrier protein. ACP is a carrier protein on which these reactions are done. Okay, so intermediate which are formed is ketoacyl, hydroxycyl, transenol, and fatty acyl. Okay, this ACP I am using because these reactions are done on a protein which is called ACP. Okay, ACP means acyl carrier protein. Okay, so how can we remember these things? We remember by a mnemonic which is king has true friend. King has true friend. So K for ketoacyl ACP, H for hydroxycyl ACP, T for transenol ACP, and F for fatty acyl ACP. Okay, so if we had decarboxylation reaction, the enzyme should be the decarboxylase. If whenever we have a reduction reaction, when we have a reduction reaction, the enzyme should be reductase. Enzyme should be reductase. In many videos I told you whenever we have reduction reaction, enzyme should be reductase, and when we have dehydration, okay, when we have oxidation or dehydration, the enzyme is dehydrogenase. So there I am using the reduction, so enzyme is reductase. Here is again reduction, so enzyme is reductase. Very easy. There is a dehydration, so enzyme is dehydrogenase. Not use not use dehydrogenase, dehydratase, because dehydration, dehydratase. Okay, so these are the enzyme in this reaction. Okay, when we have dehydration, it means water release from this reaction. When we have reduction, reduction means we add hydrogen atom. For addition of hydrogen atom, we use here NADPH, which is converted into NADP. Okay, so here is the use of NAD which also done, and in the previous video I told you the NADH is come from, yes, this is the only reaction from which NADPH, not DH, this NADPH come from the HMP shunt, also called PPP, pentose phosphate pathway. Okay, okay, here NADPH again used for the reduction and converted into NADP positive. Okay, this hydrogen is added, so reduction, and we get the fatty acyl CoA. Fatty acyl CoA is a active form of which fatty acid. Okay, so this is converted into fatty acid simply. Okay, so here the synthesis is done. If we want to degrade this fatty acid, we say the degradation of fatty acid, beta oxidation. Okay, so beta oxidation is just the degradation of fatty acid. How? This is also done in 3 steps, like this, in which we first transport acetyl CoA, then we have conversion of acetyl to malonyl, then we have fatty acid synthesis complex. Like this reaction also done in 3 part. First is the activation of fatty acid, and I I told you in the last few seconds that fatty acyl is the active form of fatty acid. So we, in the activation of fatty acid, we just convert fatty acid into fatty acyl form, fatty acyl CoA. Okay, this is CoA form. This is the activated form of fatty acid. Okay, and here ATP is used. Okay, ATP is used. Okay, in reaction. Okay. Second is the transport. You should remember this is many times asking the question that for the transport of fatty acids, for the synthesis of fatty acid, which is transporter used? Transporter is straight, which transport acetyl CoA. But in the beta oxidation, we don't have straight. We have one another thing which is called carnitine. Carnitine. This is asked in many MCQs question. Okay, so transport is done by carnitine, and carnitine transport fatty acids. Okay, and in the senses the transporter was straight and transport the acetyl CoA. So here the transporter is carnitine and transport the fatty acids. Okay, so we have done the we activated the fatty acyl CoA, then transport fatty acyl CoA with the help of carnitine. Okay, so then we have beta oxidation proper. We can say that carnitine transport fatty acyl. Okay, don't confuse fatty acyl. Okay, yeah, or fatty acid. Okay, same thing. Okay, so you should remember that carnitine help in this transport. So after this we have beta oxidation proper. What is beta oxidation proper? This is also done in the same sequence but just opposite to the beta to the senses. We have king has two friends, K for ketoacyl ACP, S for hydroxycyl, 2 T for transinol, and F for fatty acyl. Just this was the synthesis. If we done this opposite direction, this is the degradation. So very easy. So first should be the fatty acyl. So the first is fatty acyl CoA. Okay, the second one is transinol. Okay, the second one transinol. Then should be hydroxycyl ACP. Then hydroxycyl ACP. Then should be the fatty acyl ACP. Then we have fatty acyl. Okay, so you can easily remember, just reverse this reaction. Okay, and you will get these. Okay, so king has two friends. For the senses we have king K has as a true friend. So king has true friend. Okay, this is the mnemonic. Okay, in the senses we have reduction, dehydration, and reduction. But this is opposite. So it should be the oxidation, hydration, and oxidation. Oxidation, hydration, and oxidation. Okay, so this is very easy. If you know the senses, you can easily do the beta oxidation. Okay, for the oxidation I told you many times, for the reduction we have reductase, and for the oxidation we have dehydrogenase. Okay, so enzyme is dehydrogenase, fatty acyl CoA dehydrogenase, fatty acyl CoA dehydrogenase. For hydration we have hydratase, simple, which hydratase? Transinyl CoA. Okay, transinyl CoA hydratase. For the oxidation we again has dehydrogenase, which dehydrogenase? Hydroxy acyl CoA, hydroxy acyl CoA dehydrogenase. Okay, therefore the cleavage, this is the one more reaction which is extra than the those mnemonic. Okay, for the cleavage we have enzyme which is called thiolase, which just convert this ketoacyl CoA into two products, because we are degrading the fatty acid by the beta oxidation. So it should be the two product. For when we degrade one thing, there is a two product. Okay, so which two product are from? One is the fatty acyl CoA, simple. Okay, fatty acyl CoA. The second one is acetyl CoA. So what is the difference between acyl CoA and acetyl CoA? Look, when we have acyl CoA can be any carbon atom which is attached to CoA. But when we have acetyl CoA, it means two carbon. When I have two carbon, it means acetyl CoA. So we know one thing, that fatty acid beta oxidation give at the end of each step, at the end of reaction, give two carbon compound at fatty acyl CoA. Okay, and this is also asked that which of the following is we got in each end of the reaction. We have acetyl CoA which we got. Okay, okay, I think this is done here, but we are going to study how many ATPs are formed. So I told you many times, when we have dehydratase enzyme, okay, whenever we have dehydratase enzyme, there should be the formation of FADH or NADH. In many previous lecture I told you this thing, okay. So when we have dehydratase, there should be the hydrogen removal, then there should be the acceptor for it, and here acceptor is FAD positive, so it gives rise to FADH. So whenever dehydrogenase enzyme, FADH or NADH is formed. So in first reaction we have FADH formation, but we have two dehydrogenase enzyme. In second dehydrogenase enzyme, there is a formation of NADH by NAD. Okay, so let's count how many ATPs are formed. Okay, by this reaction, you should know that uh, 12 ATP, 1 acetyl CoA, 1 acetyl CoA is equal to 12 ATP. If you want to know how 1 acetyl CoA is equal to 12 ATP, see my watch my video on the TCA cycle. I show you there that 1 acetyl how can give 12 ATP. Okay. Then second we have 1 FADH, which is equal to 2 ATP, and we have 1 NADH, okay, which is equal to, very good, which is equal to 3 ATP. But this thing is not done here. Many times the question is asked about how many ATPs are formed by the help of palmitate, which is a 16 carbon compound. Okay, palmitate. If we talk about the palmitate, how many ATPs are formed? Palmitate ATP. Okay, this in the palmitate, which is a 16 carbon compound. Okay, which is a 16 carbon compound. You should know the palmitate is a 16 carbon compound. And how many 16 carbon compound this palmitate can give acetyl CoA? We know acetyl CoA is a 2 carbon compound, and simply if one asks how many we get 2 carbon compound from 16 carbon compound, we can divide 16 divided by 2, which is equal to 8. So we get 8 acetyl CoA, okay, from the palmitate. So 8 acetyl CoA from the palmitate are equal to 12 multiplied by 8, okay, almost 96 I think. Yes. And then we have, if we have 16 carbon, okay, so in you can see that at end of one step we get 2 carbon compound. If we have 16 carbon, then from 16, if 2 carbon is released, when then we get 14 carbon plus 2 carbon, this acetyl CoA. So in next reaction 14 carbon is degraded into 12 carbon and 2 carbon acetyl CoA. Then this 12 carbon is degraded into 10 carbon plus acetyl CoA, okay, and this is degraded to 8 carbon plus acetyl CoA, and this is degraded to 6 carbon plus acetyl CoA, okay, and this is degraded into 4 carbon and acetyl CoA, and this 4 is converted into 2 carbon, which is acetyl CoA and acetyl CoA. So we can see here that if we have 16 carbon, we get 1 2 3 4 5 6 7 8 acetyl CoA. And in how many steps this reaction is done? 1 step, 2 step, 3 4 5 6 and 7. So we get we degraded the 16 carbon completely in 7 step, okay. So in 7 step we degraded this, and you can if you want to get formula, you can simply say n divided by 2 minus 1. This will give you the step, how many step are in degradation of any fatty acid. N is equal to carbon number. So if we have 16 carbon number, 16 divided by 2, 8 minus 1 is 7 step, okay. If we have 7 step, and when we know in each step we get 1 FADH and NADH, so there should be 7 FADH and 7 NADH, okay, very easy. So 7 FADH is equal to, very good, we get 2 ATP from 1 FADH, so 2 multiplied by 7 is equal to 14, and we get 3 ATP from NADH, so 3 multiplied by 7 is equal to 21. If we count total how many we get ATP from palmitate. This is equal to 131. Okay, so 131 we get the ATP from the degradation of 16 carbon palmitate. This is mostly all, but the net ATP, because in the this for the activation of ATC there are 2 ATP used here, so net we get 129 because we get 129 because 2 are used in the activation.